In this video, we will see how to build a pruned tree in JMP. We saw earlier that we can keep building the tree to the level of granularity such that the terminal nodes are completely pure. So we have correctly classified every single record. But a problem with that tree would be that even though it has got a perfect classification accuracy on the training set, it will do poorly on new unseen data. So to prevent overfitting, we want to be able to prune the tree, basically scrapping off weak branches so that the tree is more robust to predictions and classification for unseen data. We set up our model as before. We go to Analyze and then Predictive Modeling, Partition. Let's move our personal loan to our Y response and move everything else except for ID and zip, and of course personal loan, to our X factor. And now one change that we'll do is that we'll use this validation column and move it to the validation. So once we do this, JMP will know that it'll be building a pruned tree and will check the tree on the validation, and then also give us the results of the tree's classification on the training set, so we can get an idea of our error in the training set as well. And the default option will still be decision trees. We click OK, and here we can just let the default setups be the way they are, and then the default options were again how many in minimum size split. We'll leave that at 5. Let's not change the defaults here. But instead of trying to build the model using the split button successively, we can just build it in one go by clicking on the Go button. We click Go here. So JMP has built the tree for us on the training set, and it also gives us the link between the splits and the R-square of the split. So even though we can go up to 20, more than 25 splits, but if you look at here, the validation data is in red, the test set is in orange, and blue is the training set. After a certain point, we do not see any gains in R-square on the validation set. So JMP will stop the tree at this 10 cutoff point. So the tree that we get will be with 10 splits, and the R-square on the training set is 0.88. And interestingly, the R-square now on the validation set is 0.89 and the test set is 0.83. So it has done a fairly good job, and this shows that the model is not been overfit because we do not see a significant drop in performance between the training and the validation set. Of course, both of these will do better than the test set because test set is completely unseen. So now let's look at some more diagnostics of this. And again, the interpretation of this is that the first split happens at income level of 95, more or less. Again, now this is different than the initial value when we had only number of observations as 1. Then after income, the next level of split happens at education. And then here it happens at credit card average. So now if we get a new data point, we can just drop it down this table and follow the rules, and we'll be able to classify with a certain probability whether our data point will be accepting loan applications or not accepting loan applications. Again, to see these rules laid out, we can go to Partition and we can click on the Leaf report. And this gives us a set of rules for the 10 splits that we can use to classify a new data. And let's see how well we did. We already saw the R-square, but let's look at the measure of accuracy by showing the confusion matrix, and we will get that by showing fit details. See the fit details, we can now calculate the accuracy in the classification. We're actually doing a very good job with this model. Our misclassification rate in the validation set is only 1. And then in the test set is also close to 1%. So this model has been able to do a fairly good job by chopping off or pruning off unnecessary branches and keeping only the ones that are adding value to our classification problem. And we can also look at how our model does in terms of the ROC curve and the lift chart. So to get those, we go to partition again, and we can see, let's start with the ROC curve, which tells us how our model does compared to randomness. So again, the top right coordinate tells us a case where the model has done an excellent job of classifying our records, and the diagonal line tells us how nature or randomness would have done that. So our model definitely has a very high ROC, and again, we will always expect the training set to do very well, but let's look at the validation. Our area under the curve for validation, again, for blue is the outcome of interest, is 0.99, which is close to a perfect fit. And then how well can we expect this data to do in unseen data? And that can be seen by gauging the AUC, or area under the curve, on the test set, and that is 0.99. So again, a fairly good fit, and GARTs generally do much better than any parametric model techniques like logistical regression or something else. It's a very powerful technique of classifying our data with a very high level of accuracy. Now let's look at the lift chart and see how we interpret a lift chart. So again, I'm going to go to the little red arrow and click on lift curve. Our interest is not on the lift curve for training, that's what the first one is, but on validation, because this is what we used to assess the model. To interpret this, we'll actually do some more calculations, and then we'll come back to this chart. So let's get back to our data table or our model and actually save the prediction formula into our data table. So I'm going to go to this red arrow again, click on save columns, and then choose save prediction formula. Once we do that, let's go back to our data table. What we see is that a new column has been added here, which is now looking at the probability of accepting the loan based on the CART tree and based on the rules that we came up with, and then the probability of not accepting the loan, and then based on the cutoff value of 0.5, will this particular person be accepting or not accepting the loan. So for this observation number 34, for example, a person whose age is 30, experience 6 years, income 18, zip code is irrelevant, we'll ignore that, family size 3, credit card average 0.9, and so forth. The probability that this person will not accept the personal loan application is 0.99, and probably that this person will accept is 0.0004, so really small. So based on the cutoff, this person will be classified as a non-acceptor, and that's what this is. And if we compare this to the actual result, this person did not accept the loan, so our model correctly predicted this individual's status. So let me just filter out only the validation set so that we can see what a lift chart is. So what I want to do is basically filter out on validation column and then just get the columns which are in the validation subsample. So I'm going to first clear all this, and then so now even though we see training and validation and test, because this is an ordinal variable, jump is giving it value labels. We can't find training or validation by text, we'll have to find the label. So to see the label, we could also right click here, we go to column info, and if we click on value label, this tells us that the value label of 0 is assigned to training, and then the value label of 1 is assigned to validation, then 2 to test. So we'll use this to first filter out all rows where validation column equals 1. So we can do that several ways by going to the rows option, looking at row selection. We could have done this here by this little red arrow. So let's start by going, or we could have done it even here. So let's go to row selection, and we say select where. let's choose validation, and this equals 1. And you click OK. So now we see that we have 1500 rows selected in the validation column. Now let's make this into a separate data table. So I'm going to click on here and then say data view. So now we have a filter of only the validation columns, 1500 validation columns in our data set. Now notice that randomly we had 10% roughly accept our loan application. So out of these 1500 in the validation set, we would expect 150 to accept the loan, because 10% of 1500 is 150. So suppose I split my data randomly into deciles, each decile or into 10 groups. Each group will have 150 people. Out of these 150 people, we would have had 10% of them accept loans, so 15. So in every bucket I can create, let's say I create 10 equal buckets of 150 customers each. In each of these buckets, we would expect 15, 15, 15 to be randomly accepting the loan, because each bucket size is 150 and each bucket has 15 people. But there's a better way of doing it, and that's what we've done with the cart tree. What we have actually gotten is, for each of these individuals, a probability of accepting or not accepting the loan. So instead of just randomly dividing the bucket, we know that in each bucket we would expect 15 people to have accepted the loan. Let's sort based on the probability our model got. I'm going to right click here and then click on sort and descending. So these are our most likely people to accept the loan, and then all the way going down in probability. Now again, remember, each bucket's size in our sample of 1500 is 150. So if I go and split my bucket into the first bucket, or data into the first bucket of 150, which is right over here, in this top risk, we are saying that 140 would be the acceptors of loan. We did not know if they accepted loan or not. Let's see if our guess was correct. And if you look at the personal loan, a significant number of these were the ones who accepted the loan. So in our top decile, a model did a really good job of identifying the actual loan acceptors. So the lift chart that we have here is essentially dividing the data set in buckets based on high risk, and then comparing that with nature, or compared to 10%, which would be only 15 in the bucket of 150. How many multiples did we correctly identify? So what is the practical implication of this lift chart? Let's say that you're working for this universal bank and your manager says that we need to send out only 300 mailing applications, and this is the data set. Figure out which 300 to choose. So if you had randomly chosen 300, we would expect only 30 of them to be accepting the loans. But by building a model and then by ranking our observations or our individuals based on the highest probability to be able to accept the loan all the way to the lowest, let's say that now we look at 20% of our percentile, which is, out of 1500 set, 20% would be 300. If we were to choose 20% of our highest risk people, our model would do almost 6 times as well as nature, roughly 5.5 times as better as nature. So the lift chart gives us an indicator of how good our model is in identifying the highest risk people compared to what nature would have done. So if you were to compare two models, we would look at both the area under the curve, the model that generates a higher area under the curve, or the AUC, also the model which would generate a higher lift for at least the top risk people. And then we can also look at the confusion matrix, which tells us the misclassification rate. So having said this, what we are finding is that the model that we have built with the pruned tree is having a much lower misclassification rate, not just for the training, but also for validation and more importantly for the test set, because this error rate gives us an indicator of the error we might expect in real life, and then validated by a very high area under the curve and then a fairly high lift chart as well.